Hello, everyone. In this session of the Students Host Actions, we introduce Dr. Martin Kaupp for the Technische Universität of Berlin. His research focused on the development of quantum chemistry methods for calculating nuclear magnetic resonance and electroparametric resonance parameters. We specialize in density functional theory, relative effect, and computational chemistry. Dr. Kaupp has awarded the Black Medal in 2001 by Waltok and many others for this successful career. Thank you so much, Martin, for accepting the invitation, and the floor is yours.
Okay, thanks, Francisco, for the kind introduction. Also for the invitation. Let me share my screen now. Does it work? Yeah, so I think you should see it by now. So last time I was in Barcelona was in person just before the pandemic in 2019, which was fun to meet a lot of friends. Now, but it's also fine now to join you here online, and I hope technical aspects will work. What I would like to do today is talk about our new density functional approaches, going to beyond the so-called zero-sum game. And showing you that I think we open some avenues for applications, but the talk will be essentially centered around the methods, but I will show some applications. So I will do an introduction on what I think are the current challenges in DFT. Will explain what this so-called zero-sum game is. Then I will focus or introduce, for those who are not familiar with local hybrid functionals, based on the exact exchange energy densities, why I think this is a very important progress in DFT and what we have done in this area a little bit. Then I will extend things to so-called range-separated local hybrids, introducing the omega LA22T functional. And then probably most exciting recent developments is going beyond this zero-sum game by introducing strong correlation corrections into these functionals. And if time permits, I will in the end even show a few very recent results on strong correlation corrected local hybrids and some magnetic properties. So let me start with what I think are the current challenges in DFT. I guess you are all familiar with the fact that the exchange correlation functional is the decisive aspect determining the accuracy of Kohn-Sham DFT, and you are also familiar with this incredibly large zoo of functionals, which makes it often difficult to choose, and also the attempts of some maybe systematic view using this Jacob's ladder by Purdue, where the functionals I will talk about today are on the fourth rung, which is the hybrid or hyper-GGA rung. And if you go to that rung, you are automatically in the realm of what is called the adiabatic connection formalism. And they are the background of introducing hybrid functionals by Becke. So I want to introduce it right now because I will base some of my arguments on this adiabatic connection. So we are talking about this lambda integration from the non-interacting reference system at lambda equals 0 to the fully interacting system at lambda equals 1. So you have the Kohn-Sham system here on the left side, then you have some kind of interpolation here, and then you go to the real system that you want to describe, and everything is done keeping the density constant along this adiabatic connection. Now, Becke actually introduced hybrid functionals by starting with a linear interpolation. And if you do that, you actually arrive at what is called the half and half functional. Probably many of you have used BH-lib, which has 50% Hartree-Fock exchange, and that's what you arrive at if you have essentially the weakly correlated limit here with a linear interpolation. And that obviously is not a very good functional for thermochemistry, etc. And then the parameterization started. You all know B3LYP and many other global hybrids. And what I want to emphasize already here at this point is that for local hybrids, we need a local version of the adiabatic connection based not on integrated energies, but on energy densities at each point in space. This has never been proven rigorously, but it's very obvious that it will exist. one can just shuffle the order of integration. And it's also relatively clear that it should work better than the global adiabatic connection. Now, what are the main challenges from my point of view in the development of DFT functionals? First one can mention is van der Waals interactions, dispersion forces. I would consider this essentially solved for most practical purposes. I'll come back to that in a second. Then among the active problems are self-interaction errors, often called delocalization errors, because we're delocalizing density or spin density. And Weithauer, Young and co-workers framed this in terms of fractional charge errors. I will explain this in a moment. And then on the other side of the coin, we have static correlation errors, often non-dynamical correlation errors. And in this framework of fractional particles, one can frame this as fractional spin errors. I'll also explain that in a moment. And those 2 points, B and C, they constitute what is called the so-called zero-sum game, because I will show also examples that it's often, if you want to improve on one, you make the other one worse and so on. And that's what we want to escape here, really. And finally, I think an aspect that is often underappreciated is we need different different requirements in different regions of space, be it near the nuclei, far away from the nuclei, in the bonds, and so on. I'll come to that in a second. Now, regarding dispersion, you are all familiar, I assume, with these atom additive corrections. We often use Grimes D4 terms now to combine with our new functionals. One can, of course, also be more sophisticated and introduce some kind of these non-local van der Waals functionals like the VV10, which are part of the, for example, B97 MV or things like that. So obviously there is still probably room for improvement, but I think for most practical purposes, these approaches do fine. Now, on the other hand, on the side of self-interaction errors and non-dynamical correlation, let me start with the fractional charge errors. Often Weithauer, Young and co-workers use the H2 plus ion binding curve as an example. Here, Hartree-Fock gives you the exact result because it's only one electron. Most density functions give you a behavior like this here, where you have a local maximum and then you go down. And that's then it dissociates to the wrong limit, because what you get is 2 H plus 0.5 ions rather than 1 proton and 1 hydrogen atom. And that's the fractional charge error. And Weithauer, Young, and also already Purdue, they modeled this just with a hydrogen atom where you seamlessly change the number of electrons from 0 to 1. And then the exact functional should give you a straight line. This is just the difference here now from the exact behavior, should be straight. But most functionals give you a convex behavior, over-stabilizing the half integer charge. And that's the fractional charge error. And in actual practice, because this is just a model, in actual practice, what you find is you have 2 delocalized charge densities compared to the real situation that how it should be. And that's a big problem, obviously, in DFT. Then on the other side of the coin, we have the fractional spin errors related to static correlation. Here we can start with the H2 binding curve, where Hartree-Fock gives a far too high asymptotic here. This is now spin-restricted dissociation curves, not allowing symmetry breaking, I should say. And then in the dissociation limit, you have too much ionic contributions. That's why the energy is too high. And this is still the case if you do DFT. Here, LDA is even a little bit better than B3L/P. So exact exchange kind of makes this worse in a way. And modeling this with fractional occupations, you can take 1 electron, but you can either do it spin up or spin down, or you can, for example, take half an electron spin up, half an electron spin down, or anything in between. And the exact functional should give you exactly the same energy for all of these configurations, and essentially practical functions give you a concave behavior. And that's then related to static correlation. And then Whitehall, Young and co-workers put this together to a so-called flat plane condition, where you have the fractional spin dimension here, fractional charge dimension with two straight lines, and a derivative discontinuity at the integer for the fractional charge dimension. And exact functionals should give you exact these two triangular planes, so to speak, connected. Also for other atoms, obviously, and molecules. And this is not the case for approximate functionals. And now comes the zero-sum game. If you try to improve by the fractional charge error by adding more exact exchange here from the left to the right, this is from a paper by Maurice Sanchez and Cohen, you improve the fractional charge error, but you make the fractional spin error worse. So static correlation gets worse. And this is the zero-sum game, as Benyanesco has called it. And that's really probably the biggest challenge in DFT right now. And I will show you approaches how we start to get out of this dilemma here. The other aspect I wanted to emphasize is we have different requirements for a function in different parts of a system. For example, if you go close to the nuclei, we know that exchange dominates over correlation. It's important for many core properties. And then you need larger exact exchange and mixtures. We know that, for example, for hyperfine couplings and things like that. On the other hand, far away from the nuclei in the asymptotic region, important for Rydberg excitations, electron affinities, and so on. Also, the correct asymptotic decay of the potential requires larger exact exchange and mixtures. And again, exchange dominates over correlation. On the other hand, if you are in the bonding region, in particular also stretch bonds and so on, left-right correlation is reasonably well modeled by a local hole that you have for semi-local exchange. And then smaller exact exchange and mixtures might be advantageous, and you want that. So you see different parts of a system require different amount of exact exchange and mixtures. And you can extend that. Let's say you go to a more complicated composite system. This is from a paper by my former PhD student, Hilke Barmann, with her co-workers. They have looked at these dye-sensitized solar cells, modeling a titanium oxide cluster and a connected organic dye. And they wanted to see how the frontier orbital levels of these two entities match. And they found, even with a very early first-generation local hybrid functional from our group, that the match is much better than, let's say, with a global or range-separated hybrid. But I would like to take this example even further and say we replace now the oxide by a real transition metal surface with strong correlations where you need to have a lot of static correlation. At the same time, you also want to model the charge transfer through the organic dye and get those charge transfer excitations, ionization potentials, and so on. And then you need small self-interaction errors. You need small fractional charge errors. And so the functional should, if you want to do this with DFT, the functional should allow you to simultaneously describe these two aspects. And that's a challenge indeed. Now, our own approaches in this field are based on local hybrid functionals, based on the exact exchange energy density rather than integrated energies. And as many of you might not be familiar with these types of functionals, I want to introduce them briefly. So the general idea is fairly simple. Instead of a constant exact exchange at mixture, say 20% in B3LYP, we have a position-dependent exact exchange at mixture. It's different amounts in different points in space, governed by a so-called local mixing function, G of R. An example is shown here with some color coding for the different regions that we want to cover. And what we are now doing is we are mixing energy density, so the exact exchange energy density and some semi-local DFT energy density. And there comes in the so-called gauge problem, because these energy densities are not fully defined. They are only defined up to a calibration function, capital G of R, that can integrate to 0. And then for a global hybrid, that will integrate out. But for a local hybrid, it will not integrate out due to this product here. And so we have to worry about this gauge problem. And one big step forward for our developments has been to introduce semi-local calibration functions that improve the matching between those energy densities and make local hybrids possible or much more accurate than before. Another aspect that I want to mention, but will not go into detail, is due to these types of integrals, we have new two-electron integrals which cannot be solved analytically. And our implementation in the turbomole code is based on very efficient semi-numerical integration techniques. So the problem of implementation efficiency is essentially solved, I would say. So I will not go into that. Now, our first, let's say, modern local hybrid that included these considerations and included our currently most accurate calibration functions based on a partial integration gauge to second order, won't go into detail, is the LH20T functional optimized by Matthias Hasel as part of his PhD thesis. The parameters of these calibration functions are fixed separately from the other parameters by looking at the dissociation curve of noble gas dimers, because we found that the gauge problem makes those two repulsive. And if you correct, then you get a much better representation. And that's all we do for that part. And then the other part is kind of optimized orthogonally. This includes a B95 meta-GGA correlation. Then the local mixing function, which we call a TLMF, that's still currently our most widely used example, which is just a scaled ratio of von Weizsäcker and Kohn-Sham kinetic energy densities. That's kind of a typical inhomogeneity parameter in, for example, also in meta-GGA functions. And then we have PBE exchange here as the semi-local variant. And if we do that and optimize this, we arrive at LH20T, and this was the first local hybrid that outperformed global hybrids for the large GMTKN55 main group test suite of Grimme and co-workers, in particular after adding D4 dispersion corrections. We also found that LH20T is among the best run, or generally the best functionals for organometallic reaction energies and barriers and so on. So it really has a wide applicability. One interesting observation early on, even with our first generation local hybrid, was that in TDFT calculations, they give surprisingly good singlet triplet excitation energies. And one example of using that is a work by Robin Grotjan as part, I think, still of his master thesis, where he set up a protocol based on local hybrids to evaluate singlet fission chromophores in a collaboration we had with Josef Michel's group in Boulder, Colorado. So that's one of the advantages. And Robin, as part of the PhD thesis, he implemented also excited state gradients for these local hybrids. And there we, for example, have been able to compute vibronic phosphorescence spectra because we get good singlet triplet excitation energies and also good vibrational frequencies. And then this is superior to some of the other functionals that have been used for these type of properties. And just to kind of show a little bit more, and I will later come back to these properties, that we have a number of properties implemented already with these types of functionals. Let me come to NMR chemical shifts or nuclear shieldings. This has been the PhD thesis of Kaspar Schattenberg. And he has implemented local hybrids into turbomole for nuclear shieldings and spin-spin coupling constants. And he has also, as part of his thesis, set up this huge main group shielding benchmark with 372 data points for light main group systems. Examples are shown here. And then we have very accurate coupled cluster reference data that we can compare to, and we can do statistics. And let's say we look at a percentage unsigned error of below 2% across all of these nuclei, which we then can compare. You see that not many functionals achieve this goal. There are double hybrids here. DSD PBE P86 is an example which does very well. MP2 does very well here too. This shows you there is not too much static correlation involved here. But of course, these types of double hybrid calculations for nuclear shieldings are fairly expensive. So it's very limited to smaller molecules, whereas local hybrids are much easier to compute for nuclear shieldings. And you see several of our local hybrids are also in this ballpark of better than 2%. And then we also observed something interesting. you see the little C's in front of the functionals here. This indicates that we have included current density response for the tau contributions, for the local kinetic energy contributions that occur both in our local hybrids and in meta-GGA functionals. And if you do that, which has not been done in earlier implementations, that's work by Caspar, then you see, for example, MN15L or B97MV also come into this ballpark and perform excellently. So that's also a new observation. So there are new tools here in the main group case, but we also went further and implemented a benchmark set based on experimental data together with my old friend Michael Bühl in St. Andrews on transition metal nucleus shifts for 3D systems. And here the challenge is much larger. You cannot do high-level benchmark calculations. Coupled cluster is not accurate here. Hartree-Fock MP2 or double hybrids are completely useless. They give you telephone numbers. So we had to look for experimental data, correct it back for some solvent effects and stuff like that. And what you then find is the challenge is much larger here indeed. So to even be below 5% relative mean absolute error across these nuclei is not so easy. We see that B3LYP, which was previously found to be the overall most accurate functional in this field, is doing the job just below 5%. But several of our local hybrids also come into this ballpark. And again, two different meta-GGAs when and only when computed with current density response also do well here. So that's also surprising. And I'll come back to these computations later on, because we now have also implementation for strong correlation corrected local hybrids and can get further improvements. So then I want to go a next step in terms of the implementation. One shortcoming of local hybrids is that they don't give you the correct long-range asymptotic potential. Even if our energy densities may be 100% Hartree-Fock exchange asymptotically, you do not get the correct potential. And that's why we have extended the implementation to so-called range-separated local hybrids, which had been suggested earlier, but Susanne first in her PhD thesis has done the first modern implementation with all the advantages of the semi-numerical integration and so on, and the first real self-consistent treatment. And she has also optimized a new functional, an extension of LA20T we call omega LA22T, which is a range-separated local hybrid. Now, how can we understand a range-separated local hybrid? I think the best way to look at this is to look at the exact exchange admixture in two different dimensions. Let's say we have the real space dimension. This could be the bond axis in a diatomic molecule. That's what I would show here now, but it's of course higher dimensional overall. And then we have the interelectronic distance coordinate along this dimension here, which is what you usually vary exact exchange mixture along for range-separated hybrids. So a global hybrid like BH-LIP would have 50% Hartree-Fock exchange in all of these dimensions. If you take a local hybrid, let's say LH20T, we have this real space dependence governed by the local mixing function, but we have no dependence in the interelectronic distance space. If we take some range-separated hybrid like the omega B97XD, we see the dependence in the interelectronic distance coordinate, but constancy in the real space coordinate. And now finally with omega LH22T, we have variation in the interelectronic distance coordinate. We have full 100% long-range Hartree-Fock exchange, which we need to get the correct asymptotic potential for example, for charge transfer excitations. But we also have this variation in the short and intermediate range in the real space dimension. And this is a very important advance here now. Makes it much more flexible, and I'll show you some of the consequences. There is further variance one can think of. You can take range-separated hybrids like this one here, and then make the omega, the range separation parameter, position dependent, or make it a density functional. Then you will arrive at locally range-separated hybrids. And you can even combine this now with range-separated local hybrids that has been suggested by Tony Meyer, and you will get locally range-separated local hybrids. So there's a lot of possibilities. I won't get into now. But let me dwell a little bit on this omega LH22T. First, we see excellent performance for charge transfer excitations, for example, for such model systems, or also for more substantial test sets like the Quest charge transfer subset, where omega LH20T performs comparably well as long-range corrected range-separated hybrids. At the same time, it retains the excellent accuracy for triplet excitations that we have with local hybrids that you don't get with range-separated hybrids. And we get also, due to the high exact exchange mixture in the core region, we will also get good core excitation. So there's a lot of advantages here. But probably the most striking observation with omega LH22T was when we looked at HOMO-LUMO energies, because often in the field of molecular electronics, organic photovoltaics, people use Kauppmann's theorem. They take the HOMO energy for the first ionization potential, LUMO energy for the first electron affinity, and the difference for the band gap. And in this field, often what people do, they use so-called optimally tuned range-separated hybrids. So they take the omega, this range separation parameter, and tune it for the system at hand to fulfill Kauppmann's theorem. So you will get the same ionization potential from Kauppmann's theorem that you would get from a delta SCF calculation, where you just take the energy differences. And that works fairly well, but then you have lost the size consistency of the approach. So each molecule essentially has a new density function. And there's even an interesting thing if you go to one molecule, but you want more than one ionization. For example, for these types of typical chromophores in molecular electronics. And then if you tune, as done here, the omega for the first ionization potential, you get excellent first ionization potential, but then the other ionizations in this outer valence spectra do not look so good compared to the reference data. Whereas if we do omega LH22T calculations, we do not tune at all. We have one parameter, 0.23, I think. And then we get everything right in one shot. You have to do many calculations here. Then if you want to get it right, you would have to tune for every ionization. And the same here for the PTCDA. And we observed this for many, many different chromophores, from atoms to large organic molecules. And this is a big advantage of this type of range-separated local hybrid, that we do not need the optimal tuning anymore to get these results. So that's a big advantage. But now comes the downside, and now I come to the zero-sum game again. Omega LH22T is actually worse for static correlation cases than LH20T, because the long-range exact exchange is detrimental for these types of cases. And this brings me now to the probably most exciting developments we have made in recent years, and that's the so-called strong correlation corrected local hybrids and range separated local hybrids. This has been mainly worked by Artur Wodinsky, a brilliant Polish postdoc in our group. Now the starting point is again the adiabatic connection here, and we can argue that this parameter AC will be 0.5 for a weakly correlated situation, and we have a straight line. It will be 1.0 for dominant of strong correlation, and you will have something like this here. And anything in between should have an AC in between. And now we have to think about a local version of the adiabatic connection. So we are talking about energy densities. And the inspiration for our approaches was really taken from some other real space models. Axel Becke had introduced in 2005 the B05 model, which is a coordinate space model of non-dynamical correlation that I won't go into too much detail, but it uses a relatively complicated comparison of exchange hole normalizations for a reverse Becke-Roussel model with exact exchange, and thereby adds kind of more exact exchange to deepen the hole. But he found that with this B05 NDC term, it does not really solve those fractional spin cases. Those strong correlation cases are not really treated well. And then he argued, okay, in this case, we only cover the potential energy of non-dynamical correlation. We are missing the kinetic energy, which is this blue area here. And we need to go back to the adiabatic connection to reintroduce this, and in a local adiabatic connection way. And then that led to the so-called B13 strong case, and then B13 in overall indeed reduces fractional spin errors. But it's a very complicated functional, very difficult to use self-consistently. Often we don't get convergence at all. Our real starting point was this work by Kong and Bräunhoff. Eliseo remembers that we shared the group with Emil Bräunhoff during our joint postdoc time in Montreal, and Emil and his colleague Jing Kong, they have implemented the KP16 approach, which takes this B13 machinery, but does this adiabatic connection a little bit differently, where they have a multiplicative function QAC of R, which multiplies the potential energy density of non-dynamic correlation. And this is kind of the interpolation along the adiabatic connection. And the decisive quantity here is a ratio between the exchange hole normalizations of the non-dynamical and dynamical correlation part. And this multiplicative scheme turned out to be most advantageous for us to transfer the ideas to local hybrids. I won't go into too much detail. I will actually now in the next transparency show you something like an end result already for range separated strong correlation corrected local hybrids, where everything has already been put together. One thing I want to mention is that in our first functionals, we used this reverse Becker-Roussel machinery, which is rather complicated. But meanwhile, Arthur has found that we can just construct this function Z, which really is the important function that monitors the importance of strong correlations in real space at each point in space. We can just take energy density ratios between a semi-local and we use actually a modified Becker-Roussel semi-local meta-GGA type functional and the exact exchange. And this ratio defines regions in space where strong correlation is important. We have damping factors that would kind of try to keep the good performance of the underlying functional for weakly correlated situations. But then we also found that in some intermediate range, delocalization or fractional charge errors are also linked to this Z of R. And so we can actually use the same quantity to define extra correction terms to try to improve on fractional charge errors. And this is only the case for open shell abnormal regions. And this was inspired by an earlier local hybrid by Purdue and co-workers, PSTS. Now, this sounds very complicated. Let me show you this final result, which really is kind of the current state of the art we have, where we have this function QAC, which is between 0.5 for weak correlation and 1.0 for strong correlation cases. So for 0.5, we get back our original local hybrid. And if it's larger, we get strong correlation corrections. Then we have the same here for the dynamical correlation part. We start from 100% exact exchange. So this middle term is we can define as a kind of non-local, non-dynamical or static correlation term. Oops, that was too fast. And then for range-separated local hybrids, we have an additional term here, which does not show up for local hybrids. And this is due to the fact that in the range-separated local hybrid framework, this middle term only has short range contributions. And we know we want to mimic something long range. So as soon as our QAC function deviates from 0.5 significantly, this switching function here deviates from 0. So this depends on the same quantities, but it goes from 0 to, in weakly correlated situations to 1 in the strongly correlated limit. And then it brings in some long range contributions. So while in the original omega LH22T, we have 100% long range exact exchange, then in areas in space where we detect strong correlations, we will reduce this somewhat. And that's then one aspect. And in our current parameterizations, we also adiabatically connect the dynamical correlation function. That's something we are still working on. Now, that was a lot of theory. How well does this work actually? And I want to show just some basic data here. including weakly correlated situations, showing you the weighted mean absolute deviations for the overall GMT-KN55 test set. And then for fractional spin errors, strong correlation errors, we use the DIS10 test set, which we have set up, which is the dissociation limit of 10 spin-restricted diatomic bond dissociation curves for main group atoms from the second and third period. And let me start actually with the functional here on the right side. This is the DM21 functional. Maybe some of you have heard about it. That was a science paper in 21. This is a deep neural network paper with probably 30, 40,000 parameters. So it's really a completely black box functional, but it has been trained to minimize such fractional spin errors, and it does so excellently. It's not that transferable to other systems as we have found, but here it's almost perfect. You cannot really compete it. And it's also very good functional, one of the best run 4 functionals for this weakly correlated situation, because similar data have been used for training as well. LH20T is also one of the best run 4 functionals, a little bit worse than this. We have here MO52XD3 that actually with this particular combination, we have still a very slightly smaller deviation here. And then we have what until recently was the most accurate run 4 functional for GMT-KN55, which is this omega B97MV with this VV10 van der Waals functional. But all of these functionals you see here, they have large fractional spin errors. So several hundred kilocalories per mole errors. That's this strong correlation situation for spin-restricted bond dissociation. And now if we take our most recent strong correlation and delocalization error-corrected range-separated local hybrids, there are 3 different parameterizations here with 3 different functional forms somewhat. I won't explain this into too much detail. We see we do better even than the initial omega LH22T for GMT-KN55 and better than DM21. And we have now substantially reduced fractional spin errors by more than an order of magnitude, even though that does not yet compete with this DM21. But I should emphasize, I think the largest number of parameters we have in these functionals is 13 compared to 30 or 40,000 in this one. So this is on a completely different empiricity scale, so to speak. And it does work very well. Now, the question you might ask is, how does this work? How do these functionals reduce those fractional spin errors? How do we get those bond dissociation curves right? And an example is shown here for N2, just picked out randomly from this DIS10 test set. And what you see is that LH20T, which is the underlying local hybrid, this is now not a range-separated one. This is now just the local hybrid itself, where we have introduced, that was one of our first more advanced strong correlation corrected ones, which has a damping factor. So we do almost exactly as LH20T for the GMT-KN55. But now you see that the large fractional spin error we get, which is twice, so that this difference here is twice the fractional spin error of a nitrogen atom. And this is now almost removed. We still have a kind of an unphysical little hump here in the middle that we are working on, and that is shared by all of these real space approaches for strong correlations at the moment. But we think we have ways of getting rid of that one as well. Now, the question is, how does this work? How do we get down here? And the interesting thing is our QAC factor in our local hybrids, our strong correlation factors, can be folded into the local mixing function. Now we can compare the exact exchange at mixture in each point in space before we add the strong correlation correction and after we add the strong correlation correction. And at the equilibrium distance here, not much happens. There are small artifacts here near the nuclei. They don't play a role. They are due to this reverse Becker-Roussel machinery, and they are gone in our more recent and modern versions, actually. But what we see is here, nothing happens really. But as we stretch the bond, out to say 3.8 Bohr, which is, I think, close to the Coulson-Fisher point where static correlation sets in, we see we reduce locally exact exchange and mixture, and even have a little bit of negative exact exchange and mixture here. Seems strange at first sight. And then as we go out to 1000 Bohr, these effects become much, much more pronounced, and we have sizable negative areas here. So that sounds strange in the beginning for a hybrid function that you would have negative exact exchange and mixture, but it makes total sense if you think about it from the form that I showed you earlier, where we start from 100% exact exchange, and this middle term models non-dynamic correlation. We enhance this middle term by having more semi-local rather than exact exchange, and this is exactly what we think is needed here. And we also suspect that functionals like DM21 do it in pretty much the same way, even though that one, I should say the DM21 is actually, in terms of the quantities that go into the training, is a range-separated local hybrid function. So there's some more complications. We still have the contributions from the switching function and the long-range contributions, and therefore, obviously, it's not quite as easy as in this case, but that's why I use this particular case to show what's going on. Now we have also in those range-separated local hybrids, we also had introduced these delocalization error corrections. I'm not sure I explained that enough. I should go back. This is this term here, which is a correction to the local mixing function only for certain abnormal open shell regions. And we can introduce just this correction without the strong correlation correction here, for example, in the omega LH22 TD rather than T. And what we see is if we look, for example, at a typical radical-cation system, which is a typical model for fractional charge errors, we see that here, even with LH20T, we still have this strange behavior that I indicated earlier. Omega LH22T, due to the long-range exact exchange, is doing better here. And the omega LH22TD, where we have this extra delocalization error correction, is doing even better, even though not perfect yet. And the way this works is we actually locally enhance exact exchange and mixture by this term. So we now have contributions for strong correlation that decrease exact exchange and mixture locally in space, even to negative values. And we have delocalization error corrections that increase exact exchange locally. Both of them can be present in the same functional for these more advanced range-separated local hybrids. And you might wonder whether that actually plays a role for real-life situations. And I want to show you just a few recent examples for this. And one area which we have worked on for decades actually is hyperfine couplings. And for transition metal systems, we found this so-called spin polarization, spin contamination dilemma, where you would need a large exact exchange to get the core shell spin polarization right, but then you run into spin contamination problems in the valence space. And an example for this is this MnO3 molecule that's still fairly small, so we can analyze it easily. And if we use B3LYP, we get significant spin contamination, and the same holds if we do the omega LH22T. So we get an S square value, which is too high. It should be 0.75 for a doublet system. And the origin is this negative spin densities, two large negative spin densities on the oxygen atoms. And then we get a 2 positive spin density on the metal center. And this deteriorates the dipolar hyperfine couplings. I'll show you the data in a moment. Now, if we just apply this delocalization error correction, we end up with a much lower S square value. And now this negative spin density out here is gone, and the positive one around the metal is more realistic. And this then leads, I don't want to discuss all those numbers. Let me just say that the dipolar hyperfine couplings come much closer to experiment. The isotropic ones, they depend on many other things. I don't want to discuss them right now. It becomes more complicated. But if we then also add the strong correlation corrections, we improve things even further. So you might wonder, how does this work? We have contributions that locally enhance exact exchange and mixture, and we reduce spin contamination. And we have contributions that locally diminish exact exchange and mixture, and they also reduce the spin contamination. How does this work? And we can analyze this again by plotting the local mixing function. And if we just add the delocalization error correction here, we see we get a local enhancement of exact exchange and mixture around the manganese atom. And what this does is it diminishes some of the delocalization, the unphysical delocalization of spin density onto the oxygen atoms. And then there is nothing that can be polarized and gives the negative spin density. On the other hand, if we just include the strong correlation terms, we get a reduction of exact exchange and mixture just around the oxygen atom. And that also reduces the spin polarization and negative spin density on the oxygen. Although actually this term seems to be a bit more effective from what we see at the moment. So both of these effects go in the right direction. We have looked at other systems. I just want to show you one more, which is a little bit more complex. It's this manganese pentacarbonyl nitrosyl dianion, where we had to model the environment in more detail, because this dianion, if you do it in the gas phase, you get even much larger spin contamination. And if you put it into the essentially solid state environment, because that's actually a complex doped into the diamagnetic host crystal with iron. And then if we use, for example, omega LH22T, we get this spin contamination, which is a little bit larger than for the MnO3 that I showed you. Now, if we now add the delocalization error corrections and the strong correlation corrections using this more advanced functional, spin contamination is essentially gone, and this negative spin density around the nitrosyl ligand has been removed. And we again see the same effects here for the hyperfine couplings. Don't want to dwell on it too much here. Again, we see that the delocalization error correction already does the largest effect. If we only have the strong correlation corrections, we do not really solve it for this particular problem. Only if we get some of the undamped versions of strong correlation corrected hybrids, we do see an effect. And we can add both of them, and then we get even better to a certain extent. Now, one aspect I want to briefly mention, because I think many people in Barcelona work on spin state differences. I want to mention briefly that we have recently set up a composite benchmark method for these types of adiabatic spin gaps due to Mark Reimann's PhD thesis work. This is a composite benchmark based on a complete basis set limit CASPT2 and a high-level MRCI correction, which then makes this essentially independent of the so-called IPEA shift that plagues CASPT2 calculations, and we expect an accuracy of about ±5 kilojoule per mole at most. And Mark has done this for these 5 typical iron 2 complexes, and then we can use this to evaluate more approximate methods. For the purpose of this talk, I want to only show a few DFT results spiced up by some recent strong correlation corrected ones, which were not yet in the initial paper. Now, let me first note that there are a number of functionals that give you relatively good overall performance. Actually, the best MAD here across those 5 complexes is due to the B2-PLIP double hybrid. Some other double hybrids are also performing reasonably well. This is kilojoule per mole. Sorry, I didn't show it here. Interestingly, this simple B97D GGA does very well. Very simple way of getting good spin state splittings in these types of complexes. Often in the literature, you find this B3 lip star with reduced exact exchange and mixture is also okay, but not as good. We actually found if we reduce exact exchange and mixture to the same amount for PBE0, that's doing even better. And several local hybrids of some first generation ones and an intermediate second generation one, they are also doing fairly well here. But my starting point here to come to the strong correlation corrections would be the LH20T. It's okay, but also not particularly good. And if we now add strong correlation corrections, we see that if we take an undamped version of the QAC factor, we do not change much. And if we take, a damped version, I should say, and if we take undamped versions, we get larger corrections. And I'll show similar results for NMR shifts in a moment. But this clearly has to be examined further. We did not find any changes due to these delocalization or corrections. So that's something we are still examining right now. Now, in the last few minutes, I want to show you some very recent results with strong correlation corrected local hybrids, not yet the range separated ones, for magnetic properties. This is again work by Kaspar Schattenberg, who has implemented this into his shielding code. But the first use was actually for magnetizabilities. This has been a collaboration with the Helsinki group of Dage Sundholm and Susi Lehtola. They had previously examined magnetizability for a benchmark set, main group systems versus coupled cluster data. And now we have examined this by strong correlation corrected hybrid. And if you look at those violin plots, you see a much, much smaller error distribution. A lot of this is due to the fact that we have now included also ozone, which is normally not included in the statistics. And then and that is improved dramatically by those strong correlation corrected local hybrids. But even some of these other systems in the benchmark get improved. And so strong correlation corrected local hybrids are the best performing functionals for this entire benchmark set so far. We have also nuclear gradients now for these types of functionals due to Arthur's work. And he has also looked at vibration frequencies of ozone, and we also get improvements there. But the main emphasis I want to place on nuclear shieldings again. Let's go back to the same benchmarks that I showed you earlier. The main group, the large NS372, and we have now a selection of functionals here, and look again at the relative percentage unsigned errors across the board. Let's say we look again at this black diamonds. And if we start now from LH20T, which is around 1.6%, you see that the damped versions do not do much here, but the two undamped ones, they start to improve things, which is a little bit surprising, I should say, because in this test set, we do not expect much static correlation to be involved. And we see that we still have maybe some remnant of the zero-sum game going on, because the undamped one, there will be somewhat worse, for example, for GMTKN55. So we are not fully flexible yet. So there's still improvements to be made, I think. Maybe more interesting is if we go to the transition metal test set, the TM70. And there we can do the same game. We start from LH20T, and we see again that damped versions of strong correlation corrected local hybrids do not improve much. Maybe this SCLH22T a little bit, but then the undamped versions are much better. And then if you look here, you see the main change comes actually from these green triangles, which have been shifted dramatically to the left, to much smaller errors, and that's the chromium subset. And the chromium subset of TM70 is based entirely on chromium 6 high oxidation state complexes and chromium 0 low oxidation state complexes. And it has been found earlier by Michael Bühl that if you add exact exchange, this difference is already too large with GGA functionals. And if you add exact exchange, it becomes even larger. And that's the problem here. And the main problems arise for the chromium 6 complexes, where we do find substantial triplet instabilities with higher exact exchange mixtures. And that is now the species where we have the largest corrections with these undamped versions. So there's clearly an improvement here, and we expect more to come as we go along and further improve those functionals. So I think this brings me to the end of my talk. I hope I have not been too slow. I wanted to briefly show these effects here. So there's a couple of slides still. For the ozone molecule, we see that, for example, compared to CCSD-T, we get these improvements, but we see an overshooting a little bit for the terminal oxygen atom, and the undamped version meets the reference values here very nicely for the for the central one. And then we have analyzed this, and I will skip this largely because I think I'm running late, where we looked at these strong correlation factors in space and analyzed where the strong correlation contributions come from. We have also looked at this fractional orbital density, because that is a measure for strong correlations in real space by Stefan Grimme that we can compare to these other functions. And we did the same for example, the chromium-6 complex, and find very similar results. Again, the undamped versions make larger corrections to the local mixing function than the damped ones. But this really is now the end of the talk. Would like to thank the co-workers. I think I have mentioned all of them during the talk. Tony Meyer, I should also emphasize, has worked and helped work on the TDFT implementation. Robin Grotian as well. We had collaborations with Helsinki and Boulder. We had some funding, obviously, and now thank you very much for your attention.
Thank you so much, Martin, for this magnificent talk. And now the room is open for questions. We'll start.
Well, I will start. Thank you, Martin, for the talk. I have one question and one comment. The question is related with this current density expansion that I think was traditionally employed in time-dependent DFT, but now you apply for this for the NMR shift. Why did you include this correction? Because it was something I think not was traditionally done.
Well, for nuclear shieldings and other magnetic properties, what people have usually done is to use a correction due to Maximov and Scuseria, which actually uses the physical current and not the induced paramagnetic current density, which is an approach due to Dobson, which is, as you said, is used in TDDFT for meta-GGAs and so on. And if you include that for nuclear shieldings, what you get is you need to solve coupled perturbed equations even for meta-GGAs, which you wouldn't do with this Maximov-Scuseria. But we found this Maximov-Scuseria to actually give artifacts. So you get, for example, paramagnetic contributions for spherical closed shell atoms, or for the longitudinal contribution in a linear diatomics or so, which should not be there. It definitely is forbidden by symmetry. But Maximov-Scuseria makes these artifacts. And we found if we do this, I mean, for a hybrid function, it doesn't make a difference because we have to do the coupling terms anyway. We have to do the coupling term. Only for meta-GGAs, it adds a little bit of computational effort. But we see that suddenly several meta-GGAs perform excellently if they have the current response. In fact, the current response, so there has always been talk about needing to do current density DFT for magnetic properties. And there has been early efforts even in the 90s by Handy, but nothing worked. And now we realize the first level on this Jacob's ladder where this actually comes into play is the third rung, where you have the tau contribution. So the tau really has to be made gauge independent, because tau itself is not gauge independent. And if you do it by Maximov-Scuseria, you will be gauge independent, but you get artifacts. And so if you do it properly with Dobson, then you get the correct result.
Okay.
And we found the same. We recently looked at TDDFT, and we found that it depends on the functional and on the type of excitation, how important these terms are actually.
And the second question is really concerning these iron 2 complexes. Basically, one of the problems is true that in many people that are trying to calculate spin energetics of transition metal complexes are using these complexes with iron 2 with a very simple ligand like water, ammonia.
As we did as well, yes.
Yeah, you did the same. But basically, in these cases, the main problem is that you don't have a right reference. When I read your paper, you compare also with some Monte Carlo. Well, there are some Monte Carlo results.
That was complete garbage.
Yeah, But now you indicate that if you compare the Monte Carlo results with your values are completely different, but were traditionally employed as the reference to check the accuracy of the methods. Then this is really a problem. Then my question is, why not change the models and for instance to use spin crossover systems where really the experimental really not in these cases you don't have really a very accurate experimental energy, but more or less which is the experimental energy that you have for the spin crossover complexes, instead to use this very simple. I know that for very expensive methods as this, I guess this CASPT2
you couldn't do those
MRCI you are limited to the size of the molecule. But maybe to go to, there are some spin crossover systems that are really small, for instance, manganosins or try to have
there has been work on that, on using experimental reference data, in particular very careful work by Marius Radon, and there's a couple more by Kaupp, I think. This is also important, but you have other complications now, because first of all, the question is, do you have energies or do you have free energies with entropic contributions? What are the solvent or environmental effects that you have? And all that has to be kind of taken out of the experiment to be then compared to kind of the computational data on gas phase molecules. So this is kind of clearly a way to go, but it also has its own problems. So this is also very, very difficult. And we wanted to for the first time, also have a theoretical benchmark that really is reliable. And as you pointed out, these diffusion Monte Carlo data were not reliable at all. We found that some of the conclusions they came up with were completely wrong. Like, for example, they used this density-corrected DFT, where you take a Hartree-Fock density and then you use some GGA functional and then you get something accurate. That's not at all true. So density-corrected DFT does not work at all here. And that's what we find with this new benchmark method. But you are right that this is limited in size, because even with the composite method that we came up with, we can probably still go a little bit larger than we have done so now, but you cannot go to systems with larger ligands, really.
But the symmetry is very important for these calculations. You take a bit of the symmetry? Or?
Not really. Well, I think... So these calculations were done with MolPro, so there you only have abelian symmetry anyway. It's possible that he certainly used D2H for the carbonyl or the isocyanide one, I guess, but not for the, I think for the water or for the ammonia, there was not much symmetry involved. So that kind of then also limits the size of system that you can do, in fact.
Okay, thank you very much, Martin.
And I should say it's not the CASPT2 which gives the problem, it's the MRCI step then, which really becomes very expensive.
Any questions? No? I have one. You mentioned a new benchmark for enhancement surface. How do you think the impact main group and transition metal nuclease?
You mean the NMR shift benchmarks?
Yes, benchmark for NMR.
Mm-hmm. So on the main group side, we use Kaupp cluster data, because that also eliminates any complications due to solvent or other environment effects and so on, or temperature, and all these things are gone if you take theory against theory comparisons for the benchmarking. And in this case, we were able to do that, and we had CCST parentheses T with a fairly large basis set, which we think is fairly well converged really for these types of systems, and then you can use it for benchmarking. For the transition metal side, you cannot do that, because even CCST parentheses T will not give you good results here. And the systems are anyway too big for doing these CCST parentheses T calculations. So there we had to rely on experimental data. And what we did, we checked relativistic effects, we checked even spin orbit effects, we checked environmental effects, and all kinds of structure optimization also plays a role. So how good are the structures? And I can say that for all those aspects, there are some effects, but they are not as large to make a big difference on any of the statistics that I have shown for these, for monitoring these different functionals. So I think the result is fairly reliable, and you can really take from these papers information about what functional to choose if you want to do, for example, a chromium shift or an iron shift or stuff like that.
Thank you. Any questions? No?
Maybe everybody is looking forward to lunchtime.
Possible. Thank you so much for this talk, and see you soon.
Okay, thank you for the invitation.
Thank you very much, Martin.